You are listening to The Vocal Technologist. Spoken tech for your ears.
Okay, so if you're working in data engineering, data architecture these days, does it ever feel like you're just playing this endless game of Tetris? Like high-stakes Tetris with your infrastructure?
Yeah, that's a good way to put it.
Right. One wrong move with, I don't know, partitioning, or you get schema drift, or suddenly there's this massive cloud bill you weren't expecting, and bam, you're buried.
Totally. The pace is just relentless.
It really is. New frameworks, formats, modeling ideas. It feels like a constant flood of information in product and data tech. So for this Product Thursdays data analysis, we really wanted to cut through some of that.
Get to the core of what's actually moving the needle.
Exactly. Distill the critical developments that are shaping data architecture, engineering, machine learning, right now. Give you those key insights fast.
And I think the big theme, the one that really jumps out when you look across all these innovations, is this shift. It's away from just managing volume.
Right. We sort of figured out how to store massive amounts of data.
We did. That battle's mostly won. Now, the focus is all about efficiency and precision. It's not just can we store it, but how do we get better query speed, more portability, sharper models, without just buying bigger, more expensive boxes?
Okay, yeah, doing more with less, essentially. Or doing more, smarter. Let's unpack that. Efficiency.
Yeah.
Where do we start? Maybe query throughput. Like, you see these companies, Datadog's a great example, handling just insane traffic. You mentioned, 100 trillion events they need real-time access to?
Yeah, that kind of scale is mind-boggling.
So how do you even manage that? Basic columnar compression, that's not going to cut it when latency is everything, right?
Yeah, wait, and that's where their Husky query engine comes in. It's really clever. The key thing is how modular it is. It completely separates the planning of a query from the actual execution.
Okay.
Which lets them handle really high concurrency and be super flexible in how they route different parts of a query. Think of it less like a monolithic database and more like a sophisticated logistics hub.
Ooh, I like that analogy. A logistics hub for queries. How does that work in practice?
So it's got these three main parts. There's the planner, which figures out the steps, builds the execution graph. Then there's the router, which is smart. It looks at the query and performance rules and decides which backend system is best for each piece. And finally, the executor just sends the tasks out to those specialized engines. So maybe one part goes to a time series backend, another part hits a standard SQL engine.
Gotcha. So it's like a traffic controller sending different types of cargo to specialized warehouses instead of one giant warehouse trying to do everything.
Exactly. That dynamic split lets them optimize every single query for the best performance.
That makes sense. Super smart execution. But okay, the data it's reading, that still needs to be efficient too. Which brings us to file formats. We've all gotten pretty comfortable with Parquet and ORC.
They're the workhorses.
For sure. But there's this new open source format making waves called F3, the open source data file format for the future. Big claim. What makes F3 potentially so revolutionary? Especially for long-term interoperability.
Right. So F3 tackles a classic problem. Technology becoming obsolete. Your reader is getting old. It is a columnar format built for speed like Parquet. But here's the kicker. It embeds WebAssembly decoding logic directly into each data file.
Wait, hold on. WebAssembly, why is Farah? Inside the actual data file.
Exactly. WebAssembly is like this tiny, secure virtual machine. By putting the how-to-decode-me logic right there with the data, the data becomes self-describing in a really powerful way. It's future-proof. So even if you have some ancient system reading the file, maybe something not updated in years, it can still decode newer encodings within that file because the instructions travel with the data. It decouples the format's evolution from the reader technology.
Wow, okay, that's actually huge. That solves the classic, my old code can't read your new file problem. But okay, sticking WASM in there, any worries about security? Or processing overhead compared to good old Parquet?
That's definitely the first question people ask. But WASM has security sandboxing built in, which helps. And crucially, the early benchmarks show F3 performing on par with, or even slightly better than, Parquet and ORC.
Really?
Yeah. The goal was zero performance trade-off for that future-proofing. It's a potential game changer for data portability, I think.
Okay, sticking with optimization, but maybe at a slightly different level. Let's talk compression. Meta's OpenZL. It's billed as format-aware compression. Sounds a bit like marketing spin.
Uh-huh.
But the idea behind it, leveraging the data structure, that seems genuinely powerful. What kind of gains are we talking about with this awareness?
It's actually very effective precisely because it goes beyond generic algorithms like gzip or zstd. OpenZL is lossless, but it's specifically designed for structured data. Think database tables, time series, ML features. It gets better compression ratios and speed because it actually uses the schema, the description of the data, to make smarter choices.
So it knows this column is timestamps, this one is user IDs, this is free text.
Exactly. And it picks the best compression strategy for each specific field type or even column. And they've cleverly designed it so there's still a single universal decompressor needed on the other end.
Ah, that simplifies operations.
Greatly. Even if the schema changes, they use an offline training step to create these data-specific compression models so it adapts really well.
Okay, so we've got smarter queries with Husky, potentially future-proof files with F3, better compression with OpenZL, all boosting raw efficiency. But efficiency also needs structure, right? Consistency, which takes us to the Lakehouse layer, the big battleground. Apache Iceberg versus Delta Lake versus Apache Hootie.
Yeah, this space is definitely heating up. And it shows how mature the Lakehouse idea has become because honestly, they all deliver the basics now. ACD transactions, time travel, schema evolution. You kind of expect those.
So where do they differ? What's the fight about?
It's mostly in how they handle updates, indexing, and maybe ecosystem integration. Hootie, for instance, is really strong with its merge-on-read capabilities and advanced indexing, great for scenarios with lots of frequent small updates.
Yeah, okay.
Delta Lake obviously has tight integration with Databricks, features like Z-ordering, which is basically multidimensional clustering for faster reads. But some of those optimizations are proprietary or experimental. Iceberg tends to lead on things like partition evolution flexibility and broad read-write support across engines, but maybe requires a bit more hands-on metadata maintenance sometimes.
Right. Okay, so for someone actually running this stuff, maybe using Iceberg, let's get tactical about costs. If I'm updating data frequently, why is the choice between using merge into versus insert overwrite such a big deal for my cloud bill?
Oh, this is absolutely critical. Understanding this can save you serious money. The short answer is, you should almost always prefer merge into, especially with a merge on read or more strategy.
How's that? Insert overwrite sounds simpler.
It sounds simple, but here's the problem. Insert overwrite rewrites the entire data partition every single time you need to update or delete even just a few rows within it.
Wait, seriously, so if I have a partition with, say, 1,000,000 rows and I just need to change one?
Yep, you pay the I/O cost and the storage cost for rewriting all 1,000,000 rows again and again.
Ouch, that sounds incredibly expensive and slow.
It is, especially in the cloud where you pay for every byte moved and stored. More, which merge into typically uses, is much smarter. It writes the changes quickly as small delta files. You append these changes.
Okay.
The merge cost is deferred until someone actually reads the data.
Right.
So you avoid those massive costly rewrites during the write operation.
Makes sense. Is there a downside?
The trade-off is you do need to manage compaction. You have to periodically merge those small delta files into new base files to keep RAID performance good.
Right.
So there's an operational task there.
Right.
But the immediate savings on write I/O and storage usually make that trade-off well worth it.
That really highlights the shift, doesn't it? Smarter operations, not just brute force scaling, which actually leads perfectly into this other trend, kind of a counter trend. This single node rebellion.
Yes. This is fascinating. You have tools like DuckDB and Polars directly challenging the big distributed systems, Spark, Databricks, etc., for a huge chunk of common analytics work.
How are they pulling that off? Isn't everything big data?
Well, that's the core insight.
Yeah.
Turns out, most data isn't actually big data in the way that truly requires massive distribution. Modern single machines, especially cloud instances, can have enormous amounts of RAM, super fast NVMe storage. They are incredibly powerful.
Right.
And the cost curve is shifted. For many workloads, the cost and complexity of managing a distributed cluster now outweighs the benefits. Going with the powerful single-node solution like DuckDB is simpler, cheaper, and often just as fast, if not faster. It's a direct response to rising cloud costs and complexity.
Okay, so infrastructure is getting leaner, smarter. Files are getting more portable, maybe even self-describing. We're optimizing writes. We're even questioning if we need massive clusters all the time. Now, how do we turn this efficient data into actual business value? Let's pivot to AI. We're seeing these foundation models for tabular data emerge.
Yeah, the AI world is finally catching up properly with structured tabular data. Models like TADPFN, cart, eat, Tabular 8B. They're showing really impressive results for zero-shot or few-shot predictions directly on tables.
How are they doing that? Better than something like XGBoost?
On certain types of data sets, yes. Especially small to medium-sized ones with mixed data types. They use transformer-based architectures similar to LLMs.
Ah, okay. Attention mechanism.
Exactly. To better understand the relationships between columns, not just within them. That gives them an edge over traditional methods in some cases.
But there's always a but, right?
There's always a but. And here it comes back to efficiency. These foundation models are computationally hungry.
Right. Transformers aren't cheap to run.
No. So scaling them up for really large production data sets where inference speed and cost are paramount, that's still a major hurdle. The power is there, but the practicality for huge scale isn't quite there yet. That trade-off is very real.
Okay, makes sense. Let's zoom out to the business side then. Accelerating AI, ROI, teams are under pressure to show value, but things get stuck. You mentioned pitfalls earlier, data silos, QA issues, garbage tokens. What are these things that trip teams up?
The biggest hurdles are often internal and process related. Data silos are classic. Marketing has their data, sales has theirs, they don't talk. Vague business requirements, what problem are we actually solving? And QA inefficiencies. That garbage token idea refers to bad data getting into the model training or maybe malformed inputs, missing values handled poorly, stuff like that. It pollutes the results. Or failing to monitor model drift versus data drift effectively.
So bad data in, bad predictions out, and slow feedback loops.
Exactly. You end up fixing expensive problems late in the game. The best practices really emphasize lean AI, focusing on cost-effective solutions, getting user feedback super early, and building models that are performant for the specific task, not just picking the biggest, fanciest model off the shelf.
And getting that data quality right from the start.
Proactively, not just reactively cleaning it up later.
You know, sometimes the biggest misalignment isn't even the model. It's just basic definitions, everyone calculating the same metric differently. That's where the semantic layer comes in, right? It seems to be gaining a lot of steam.
It's becoming critical.
Yeah.
Because it solves that fundamental misalignment. A semantic layer standardizes metric definitions. Finance, marketing, product. They all define active user or revenue the exact same way, using the same logic, because it's defined once, centrally.
Takes the ambiguity out.
Completely. No more meetings arguing about why the numbers don't match. Tools like dbt's semantic layer, Malloy, Snowflake's recent open standard initiative, they're all pushing this. Usually it's config files, often YAML, ensuring that same logic runs everywhere.
Okay, standardization is key. But connecting this back, you see all this tooling, these layers, and you also see vendors consolidating rapidly. You had a word of caution about that.
Yes, absolutely. Be critical. We're seeing major vendors push these unified platforms. It sounds great, one vendor, everything works together, but often this is just consolidation masquerading as unification. Meaning it can lead straight to vendor lock-in. They promise simplicity, but you might find yourself trapped by proprietary APIs, rising switching costs if you want to leave, difficulty getting your semantic definitions out, or even high data egress fees.
Ah, the golden handcuffs.
Precisely. My advice is always, prioritize open standards. Look for composable tools with clear interfaces. That gives you the flexibility to swap components out later when something better or cheaper comes along, which, let's be honest,
happens all the time in this fuel.
All the time. Long-term portability and flexibility are way more valuable than the perceived short-term simplicity of a locked-in stack.
That is really crucial advice. You need that freedom to adapt. Okay, so if we boil all this down, the big takeaways seem to be this relentless focus on efficiency and portability. It's not just about grabbing more data anymore.
Not at all.
It's about making every bit of data smarter, lighter, faster to query, easier to move, whether that's clever compression like OpenZL, smarter updates with merge on read, or even these self-describing files like F3.
Exactly. Making the data itself work harder, making the infrastructure leaner.
So maybe a final thought for people to chew on.
Okay, here's something interesting. We talked about F3, these potentially revolutionary open source self-describing file formats. And we talked about the single node rebellion tools like DuckDB getting incredibly powerful.
Right.
What happens when those two trends really collide? When these super advanced open file formats make it trivial for powerful single node tools to handle workloads that we used to think absolutely required massive proprietary cloud data warehouses.
The open format enabling the single node to challenge the giants even more directly.
That convergence, that tension between open format innovation and single node compute power, I think that's where the next really big breakthrough is going to happen. Watch that space.
Fascinating. Definitely something to think about. Build smart, everyone, not just big. Thanks so much for walking us through all this.
My pleasure.
And thank you for joining us for this look at data architecture trends. We'll catch you next time.
Spoken Tech for your ears.